A computer program does not keep all of its pages, chunks of memory, in RAM at once because RAM is limited, just like a small backpack cannot hold every book you own. The operating system loads only a few pages into frames, fixed size slots inside RAM. When the program asks for a page that is not already in a frame, the hardware raises a page fault, similar to reaching for a book that is still on the shelf. The OS must then bring that page from the slower disk, the shelf, into a free frame. If every frame is already occupied, the OS must decide which page to throw away, evict, to make room. This decision is called a page replacement policy. The goal is to keep the number of page faults low because each fault costs time. Disk access can be 10,000 times slower than RAM. FIFO replacement algorithm operational steps and data structures. FIFO stands for first in, first out. Imagine a line of children waiting for a slide. The child who entered the line first goes down the slide first. In memory management, each frame remembers the time it was filled. The algorithm works like this. When a page is needed and it is not in any frame to page fault. If there is a free frame, place the new page there and record the current counter, for example 123, as its arrival time. If all frames are full, look at the frame with the smallest recorded time to the oldest page and replace it with the new page, updating the time stamp to the current counter. The data structure can be a simple queue. Enqueue a page when it is loaded, adds to the back. Dequeue a page when a replacement is needed, removes from the front. Only the order matters. We do not need to know how often a page is used. Visualization: think of a line of cups on a shelf. When the shelf is full and you need a new cup, you take the cup that has been on the shelf the longest and replace it. The fault rate, represented by capital F, is the fraction of references that cause a fault. F equals the number of page faults divided by the total number of page references. For first in, first out, the exact number of faults depends on the reference string and the number of frames, denoted by N. A useful example uses the reference string 1234, 125, 12345, and 3 frames. Step 1, reference 1, frames after operation 1, fault yes. Step 2, reference 2, frames after operation 12, fault yes. Step 3, reference 3, frames after operation 123, fault yes. Step 4, reference 4, frames after operation 234, page 1 evicted, fault yes. Step 5, reference 1, frames after operation 341, page 2 evicted, fault yes. Step 6, reference 2, frames after operation 412, page 3 evicted, fault yes. Step 7, reference 5, frames after operation 125, page 4 evicted, fault yes. Step 8, reference 1, frames after operation 251, page 1 already present, no fault. Step 9, reference 2, frames after operation 512, page 2 already present, no fault. Step 10, reference 3, frames after operation 123, page 5 evicted, fault yes. Step 11, reference 4, frames after operation 234, page 1 evicted, fault yes. Step 12, reference 5, frames after operation 345, page 2 evicted, fault yes. Total faults equal 9, total references equal 12, so the fault rate equals 9 over 12, which is 0.75. This shows first in, first out can be far from optimal, especially when the same few pages are reused often after a long gap. Optimal replacement algorithm: Bilaty's theoretical policy and proof of optimality. The optimal, also called Bilaty's optimal, algorithm says, when a page must be evicted, remove the page whose next use will be farthest in the future or never used again. Think of a librarian who knows exactly which books you will need later. They keep the books you will need soon on the shelf and put away the ones you won't need for a long time. Proof of optimality sketch. Consider any moment when a replacement is required. Let E be the page the optimal algorithm evicts, farthest future use, and A be the page another algorithm evicts. If A equals E, both algorithms behave the same for this step. If A not equal to E, then E will be needed later than A replace A now. When E is finally needed, the optimal algorithm will have to load E, causing a fault. The other algorithm would have already had E in memory, so it cannot have fewer faults up to that point. By repeatedly applying this exchange argument, Any deviation from the optimal choice cannot reduce the total number of faults. Thus, the optimal algorithm yields the minimum possible fault count for a given reference string. Note, it is impossible to implement in real time because the future is unknown, but it serves as a benchmark. Optimal algorithm illustration: detailed calculation on a representative reference stream. Use the same reference string as before: 1234125 with 3 frames. We look ahead each time a fault occurs and evict the page whose next use is farthest. Step 1: reference 1 frames before empty bracket close bracket fault yes, load 1 to 1. Step 2: reference 2 frames before 1 fault yes, load 2 to 1, 2. Step 3: reference 3 frames before 1, 2 fault yes, load 3 to 1, 2, 3. Step 4: reference 4 frames before 1, 2, 3 fault yes, evict 3 farthest to 1, 2, 4. Step 5: reference 1 frames before 1, 2, 4 no. Step 6: reference 2 frames before 1, 2, 4 no. Step 7: reference 5 frames before 1, 2, 4 fault yes, evict 4 farthest to 1, 2, 5. Step 8: reference 1 frames before 1, 2, 5 no. Step 9: reference 2 frames before 1, 2, 5 no. Step 10: reference 3 frames before 1, 2, 5 fault yes, evict 1 or 2 both never used again to 3, 2, 5. Step 11: reference 4 frames before 3, 2, 5 fault yes, evict 3 to 4, 2, 5. Step 12: reference 5 frames before 4, 2, 5 no. Total faults equals 7 steps: 1, 2, 3, 4, 7, 10, 11. Compared to FIFO's 9 faults, the optimal algorithm saves 2 faults, demonstrating its superiority. Explanation: comparative metrics: fault counts, throughput, CPU overhead and memory utilization. Metric: FIFO optimal theoretical. Fault count 9 in example, 7 in example, always less than or equal to FIFO. Throughput: useful instructions per time lower, because more time spent handling page faults higher, fewer faults to less waiting for disk I/O. CPU overhead: very low, only a Q pointer update per replacement O of 1 time, very high, needs to scan future references or maintain a large look-ahead table, which is impossible at runtime. In practice, approximations, for example LRU, are used, costing O of 1 log n with hardware support. Memory utilization: simple, only the frames themselves. Extra data structure is a queue of size n, requires extra structures to store future use information. Theoretical, only not realistic for real hardware. Interpretation: for a child, FIFO is like a cheap, fast-to-make toy that works okay most of the time. The optimal algorithm is a perfect robot that knows the future. But building such a robot would need a crystal ball, so we do not actually make it. Practical considerations: implementation cost, hardware support, and real-world suitability. Implementation cost: FIFO needs only a pointer to the oldest frame. This can be done in a few lines of code and a single integer counter. No special hardware is needed. Hardware support: modern CPUs provide a TLB translation look-aside buffer that often uses hardware-assisted LRU approximations, not FIFO. Some systems expose a page replacement algorithm register that can be set to FIFO for simple embedded devices. Real-world suitability: FIFO is used in very small or deterministic environments such as microcontrollers, early Unix versions, where predictability is more important than optimal speed. In desktops and servers, algorithms like LRU clock or a RC are preferred because they give better fault rates while still being implementable with modest hardware assistance, such as reference bits counters. Trade-off: choosing FIFO saves development time and CPU cycles, but may cause many extra disk reads, hurting overall system performance. The choice depends on the cost of a page fault disk latency versus the cost of a more complex algorithm such as extra memory for counters, extra CPU instructions. Explanation: limitations and extensions: anomalies, hybrid strategies, and approximation techniques. Anomalies: FIFO suffers from Bilaty's anomaly: increasing the number of frames can sometimes increase the number of faults. Example: Reference string 1234125 gives 9 faults with 3 frames but 10 faults with 4 frames under FIFO. Hybrid strategies. To avoid anomalies, operating system designers combine ideas. Second chance clock gives each page a second chance bit. Pages are inspected in FIFO order, but a page with a recent reference bit set is given a new chance and moved to the back of the clock hand. This mixes FIFO order with recent use information. Approximation techniques. True optimal replacement is impossible, so we approximate. LRU least recently used approximates optimal by assuming that pages used farthest in the past will be used farthest in the future. LRU2, LFU least frequently used, and ARC, adaptive replacement cache, further refine the guess using extra counters or multiple lists. Practical extension. Operating systems may employ working set models that monitor the set of pages used in the last tau milliseconds and allocate enough frames to hold that set, thereby dynamically adjusting the number of frames per process. Conclusion for a child. Think of page replacement like deciding which toys to keep on a small shelf. FIFO just removes the oldest toy, which can sometimes make you lose a favorite toy you will need soon. Smarter ways, LRU clock, watch which toys you play with most often and try not to throw those away. The perfect way would need a magic ball that tells the future, but because we don't have that, we settle for clever guesses.